Chapter 10, we're going to look in this particular video at some of the ideas around liquids and solids. What are they, and why are some chemicals liquids at room temperature, others solids, and others gases? What is it that affects the freezing point and the boiling point of chemicals and causes them to be so much different? Such a wide variety. And so to really understand this, we have to be sure you understand what we mean by kinetic molecular theory. Now, kinetic molecular theory is simply, remember, kinetic is motion, and molecular, of course, is molecules. So how are molecules moving with respect to each other at different temperatures? And how does that explain solids and liquids and gases? And how does that affect how solids turn into liquids and liquids turn into gases? And remember also that the definition of temperature is average kinetic energy. So higher temperatures result in higher kinetic energies, and so if you have a solid and you add more kinetic energy, eventually you'll get to a point where that solid will, the particles in that solid will have enough kinetic energy to overcome any attractive forces that are holding them together, and they break apart and become a liquid. And liquids are, if you keep increasing the kinetic energy, keep increasing the temperature, eventually those liquids will fly apart and turn into gases. And so I hope you picture gases as particles where the kinetic energy is much greater than the attractive forces, and so we don't really see a lot of attractive forces between gas molecules, and they tend to zoom around and not really be affected by each other. Liquids we think of as having less, the kinetic energy is not sufficient to overcome some of the attractive forces, and so we end up seeing the results of those attractive forces and having groups of liquid molecules that are more attracted to each other, and so we have fairly strong forces in liquids. And in solids, the kinetic energy compared to the attractive forces between the particles, the kinetic energy is not large enough to move these with respect to each other. They move, they vibrate in place, but the attractive force is much larger than the kinetic energy. So that's kind of our kinetic molecular theory description of gases, liquids, and solids. So to get an understanding of why there's a difference between the melting points and boiling points of one chemical compared to another chemical, let's look at the polarity of molecules and the dipole moment of molecules. Now, you've been studying this, you've done some assignments dealing with this, so you drew the Lewis structure of these things, and you looked at how polar these molecules were. We talked about their shape. You learned to write the Lewis structures and understand the shape of these different chemicals. So we're just going to zoom on through this, and actually I think we're going to zoom on even past this. So here we're looking at three chemicals, and if we were going to compare the freezing points of these, I think you know which one would have the lowest freezing point. Would it be ammonia, or would it be water, or would it be CO2? Well, I think you know, I think you would be able to tell me that the chemical with the overall polarity being so small Here we have a number called the dipole moment is 0, because these, even though they're polar bonds, they are very symmetrical. They offset each other, so the molecule is nonpolar. It is going to have the lowest freezing point. We're going to have to cool it down, get the least kinetic energy in there to make these so they have enough attraction to actually remain a solid. And so it has to get really cold, really low kinetic energy to become a solid. Water, compared to ammonia, you see here a difference in their dipole moment. Water, you don't have to get it very cold to turn it into a solid. It has the lowest of these three. It has the highest boiling point and the highest melting point, because the particles, you have to put in more kinetic energy to make the solid melt. You have to put in more kinetic energy to get the liquid to evaporate, because the particles are more attracted to each other. So really it comes down to how polar is the molecule. But here we have a couple molecules that when we analyze them are going to turn out to be non-polar. Which one of these will have the lower freezing point and the lower boiling point? Well, it turns out that methane will have the lower freezing point and the lower boiling point, and it has to do with the fact that these hydrogen do not have a bunch of extra electrons hanging around on the outside compared to these chlorines. These chlorines have a bunch of electrons out here that can slosh around. At least that slosh is my term. I picture it like water in a big bucket, and the more water you have in the bucket, the more it sloshes when you carry it. Well, the more electrons that are on the outside of a molecule, the more they can slosh around. And it turns out, and we'll look at this in a future slide, the more it sloshes, the greater the possibility that it'll slosh and cause a temporary negative pole and a temporary positive pole in the molecule. And so they'll be attracted more, and the more they're attracted, the higher the freezing and boiling points will be. The more energy you have to put in to overcome that attractive force between the molecules. And I think we're going to go to the next slide here. Oh, well, I guess we could look at these. Of course, these dipole moments for these two compounds are pretty close. They're going to have boiling points that are pretty close to each other, but they'll be a little bit different. Which one would have the higher boiling point? Would it be the one with 1 Cl or the one with 3 Cls? So the greater this dipole moment, the more energy has to be added to make the substance boil. So this would have the greater boiling point and the greater freezing point. It also turns out that it has more electrons that can slosh, and we're back to our sloshability. Well, we'll learn a better term for that than sloshability. I don't know if you'd get by writing electron sloshability on a test or not. I don't think so. We better learn a better term. So there are several forces that occur between molecules. Now, we're not talking about chemical bonds. We're talking about just attraction of this molecule for this molecule, because there's an attraction between these positive and negative poles. Opposite poles attract each other. So what causes these forces, And how do they exhibit themselves in your everyday life? Well, the forces we're really going to focus on are these three: hydrogen bonding, dipole-dipole, and dispersion forces. Now here I've listed them from strongest to weakest. Hydrogen bonding is the strongest, and so chemicals that exhibit hydrogen bonding have higher melting and freezing points because you have to put in more energy to overcome this thing called a hydrogen bond. It's not a chemical bond, it's simply a bond between an attraction between neighboring molecules. So let's look at these forces plus maybe one more. Here on this slide, they're listed in with the weakest force at the top and